let's let's go ahead and get started. Um, so, as always, before we begin, first of all, very wise decision coming to lecture today. Uh, Today and Wednesday is going to be stuff that's not really well covered in the book, and so it will be especially important to be here and to ask questions and to make sure you understand everything, as it will definitely be represented on the final, for sure. Um, and as always, before we get started, any questions? Anything on anyone's mind? Yeah. Yeah. Yes. Yeah. So just so you know, like what we're doing it for the first time ever, actually, this way, where we're just splitting it into an in-person part on Monday, and then again, just to remind you all, of course, it'll be in person on Monday. Same rules as the midterm for the in-person part. We'll still have lecture for sure on Wednesday, but then the remainder of the final will be due Friday night. And we anticipate that the take-home portion will be a lot shorter than in the past. And also the in-person part will be a lot easier than what you see in the finals, but still like roughly the same kind of difficulty, but totally different. So as you can see already from like the two exams that we gave out, like they're pretty different from each other, right? So just be aware that that's how things always work. Yes.
For whose class was that? Because I saw like a bunch of professors contribute cute drawings and everything.
So they were my TAs at that time. So Professor Korb, now professor, she's going to be a professor actually at Pepperdine. She's joining Pepperdine in the fall. But yeah, she was my TA. She's my PhD student. And then Paul was also my PhD student and my TA. Yeah, as you can see, there's a significant difference in ability among drawing in drawing capabilities between me and my TAs.
I saw the automaton doggo.
Yeah. Yes, the doggo wisdom. But sorry, did you have? Oh, you were just asking. Yeah, they were not professors. They were my TAs. That's the answer. Question.
Another question I had is the in-class finals first one, which is on next week on the 9th, right?
That's right. On the Monday, this coming Monday, 1 week from today.
And then so that one's in person, and then we'll have the take-home exam due on the 13th.
On Friday at midnight.
Okay.
Yep. All right. Okay, lots of hands in the air, which is good. In the back.
So is the main focus going to be transitions for both section exams, or how are they setting this out? Is it like
Yeah. So as I've said before, like we anticipate that the final exam will be extremely heavily biased towards the post-midterm material.
are the concepts covered on the in-person versus the take-home going to be widely different, or is it just flow out throughout the semester?
I mean, roughly speaking, we're coming up with problems, and the problems that we think are easier, we'll put on the in-person. That's the way we're thinking about it. Yeah.
So to clarify, Wednesday during lecture, are we just reviewing the content?
No, not at all. Totally new stuff. Yeah. Totally new stuff on Wednesday next week. Yeah. Okay, yes.
So is the Wednesday content going to be on the midterm, and how long do you expect the take-home midterm to take?
Final. Yeah, no, so the material we'll cover on Wednesday of next week will not be on the final at all. The material we're covering this Wednesday is definitely going to be on the final, for sure. Yeah, yes?
How are the two parts of the final going to be weighted? Is the take-home going to be weighted more?
Approximately equal. Approximately equal. Yeah.
You mentioned this briefly before, but how long do you expect us to be working on the take-home final? Like, how long should we be spending on it, do you think?
It's a good
Is it
question.
gonna be closer to like 10, 12 hours, or is it going to be like 4 hours? Like, you can do it in one sitting.
Good question. In the past, as you guys have seen, like I usually tell the students to take about between 10, 12, sometimes 14 hours, something like that. We will have such a time limit again this year. I haven't yet decided exactly what it will be, but anticipate it'll be at least 8 hours.
Wait,
Yeah.
so the time limit is from when you download the file, or is there like a timer, or are we just supposed to like time ourselves?
This whole class is on the honor code, and I trust you guys. So think about it as the time that you are actively spending on solving it. If you're dreaming about the problems, I hope that you do, does not count. Okay, that's absolutely free. Does not count against the time limit. Yes.
And the in-person class, 3 hours?
Yeah, 2 hours. It's the same rules as the midterm. So we'll start exactly at 6, and you have until 8. Yes.
Will the in-person final be released after the exam, or will it be released on that day, like in the morning?
Good. Yeah. So we'll actually release right after the in-person. Is when we'll release the remainder of the take-home. Yeah. Just because I don't want you guys to have to do many things in your brain at once. Sorry. Just give me 1 second. I saw a hand up there somewhere. Okay. Maybe just wait a little bit. Yeah.
Oh, are we allowed to use like latex, or can we handwrite the take-home final as well?
Yeah. The take-home you can. The take-home the rules are you have to work on your own, right? So, but otherwise you can
It's our
treat it like a homework. Yeah.
And when will it be released again?
Just after the in-class portion. So basically Monday night. Yeah. Yeah. And again, the reason for that is because I don't want you guys to be thinking about too many things at the same time. That is the objective. And yeah, again, like free advice, definitely think about every single lecture, that has come after the midterm, and like make sure that you feel very confident for all the lectures. Okay? Yeah.
Is this also going to be like a 40 average, like aim? 50 average?
I'm very reluctant to answer this question. It is my intention, such as it is, for it to be easier than the midterm. Okay, but the material is much harder, right? I think the material we've covered post midterm is significantly more mind bending, right? And I'm aware of that. And that's why it's like really important that you guys feel like you've mastered it, because it's only with mastery then you can then take on variants, right? Any other questions before we get started? So I know there's one question over there. Yeah.
So I just want to let you guys know, you guys can pick the chocolates if you want, and the purpose that we bought the chocolates is because, there's a lot going on right now in the Middle East. I know the conflicts, and sometimes it is hard for us to understand the situation. But I just wanted to let you guys know, as Iranians, we're not upset that the U.S. has attacked us, and we're absolutely happy that the Supreme leader is dead. So I just wanted to make that awareness so you guys can make sure everyone is on that page. So yeah, just feel free to grab chocolate, and that would be like a way to share our happiness with you.
All right. Okay. So with that in mind, let's go ahead and get started. All right? Let's get into it. So we will start just where we left off last time. Okay? So remember now, like we have this incredibly powerful tool, right, that we proved last time, which is extremely important. And I hope you guys feel extremely comfortable with the proof of it, which is the recursion theorem, right? We thought it through step by step, and I think every step made sense. Hopefully, you guys all agree with that, right? And the power that it gives us is that now we can directly implement this idea of like a Turing machine being too powerful to exist, right? So like with self-hating Turing machines, right, we were able to directly argue that a decider for self-hating Turing machines is just too powerful to exist. Like it just contradicts its own self, right? Like a decider for self-hating Turing machines contradicts basically the definition of self-hating Turing machines and the fact that it's a decider, right? In a similar way, with the power of the recursion theorem, we can kind of take that idea to a huge variety now of problems. And we're going to see that today. So that's what today is going to be about. And my aim is that by the end of lecture today, all of you will be lean, mean undecidability machines, okay? Like you will just feel like, oh yeah, I can instantly prove things that are undecidable, all right? That is my goal for all of you, all right? So let's begin by just recalling what we were doing. So remember we had defined this loop language. I'm going to modify it slightly just because I want it to be a little bit simpler. So I'm going to call it loop epsilon. Loop epsilon will consist of Turing machine descriptions such that m on input epsilon loops. Right? So this was the suggestion that was made last time, right? And let's just go ahead and prove that this is undecidable. And you guys all saw this proof last time. So we're just going to be basically remembering it. And hopefully you guys all remember it and can help me do it. So how should we get started? What's the beginning of such a thing? Yes? Suppose not. Right? Of course. We always start with suppose not. Right? And that means we're assuming that it's decidable. Right? And so we say, universe, give me a decider for the sake of my proof. Right? So that means that there exists a decider D for loop epsilon, right? And again, just like always, right? Just like we saw when we were proving like the pumping lemmas, or when we were using the pumping lemmas, right? Like when we ask the universe for something, the universe just gives us like, you know, the decider, but it doesn't tell us anything about it except for the fact that it's a decider, right? So we have to make sure that our proof handles every possible way this decider could work, right? Just a reminder, this is like how all of these proofs by contradictions will work. Whatever you get from the universe, you have to take care of every possibility of how it acts, right? Because we don't know what the universe gave us, right? Cool. So we have in our hands this decider, right? And now we are going to use, oh, I guess I should have asked, whatever, you guys remember this. So we are going to use D as a subroutine to build M, okay? And M is going to be this like self-contradictory machine, right? So let's define M. So we are building, okay? We build M. M, let's say, takes some input X, and then like here's the code of M that we're going to fill in, right? And now again, keep this in mind. D is a thing that the universe is giving us, right? But we are building M explicitly, except for the fact that it uses D as a subroutine, right? So like all the code of M will be completely explicit. It's only the use of D that we don't know, right? We don't understand what's going to happen with it, right? All right, so what should we do? How should the machine start? Yes? Yep, so yep, via the recursion theorem, right? We know that without loss of generality, we can assume that our machine just starts with its own description and some auxiliary tape, right? Work tape, whatever we call it, right? So awesome. So we just let that be alpha. Excellent. Okay. So we have our own description, right? Which is, again, like I always want you to like think about how cool, and definitely tokens for both of you for your contribution so far, but like think about how cool and like mind-bending this is, right? That like we haven't even decided what our machine is going to do yet, because we haven't finished writing it out. But we already have our own description. Because like we know we're going to eventually finish writing the machine. and alpha will just be our own description, right? That's like the insane power of the recursion theorem, right? All right, so we have our own description, yeah? Yep, so we can run d of alpha, is that what you said? Okay. Again, I did change the definition of loop epsilon, so now it's only the description of a machine. That makes things a little bit easier, right? Excellent, right? And now, again, the universe gave us the decider D, so we don't know what it's going to do exactly, right? And so we better deal with all the possible cases here, right? But absolutely, that's worth a token, and right next to you, yeah? Okay, so if except, right? And today I'm just going to do it a little bit differently. Maybe instead of using comments, I'm just going to like think of an analysis on the side. Okay? And yeah, so we know that if, so here we have sort of case 1, right? And this case 1 will just be exactly if this is true, right? So case 1 is if d of m accepts, right? So yeah, so if d of m accepts, what does that mean? Like, yeah, it means, and I'm just going to write it like pedantically, right? So by the definition of a decider, right, this implies that m is a member of loop epsilon, right? By definition of decider, right? And if it's in loop epsilon, this means m of epsilon loops, right? By definition of the language loop epsilon, right? Excellent. Okay, so that's our analysis so far. So what should we do in this case? Yeah, just, we're the rebellious teenagers, Dad just told us, D for dad, told us, oh, you're going to loop, right? And then we just do the exact opposite. So in this case, we just halt, right? And so at this point, we can say, okay, but m of epsilon halts by construction of m, right? Like the code of m literally tells us that this machine is going to halt, right? And that's just a contradiction, right? Excellent. Definitely worth a token. Any questions about this so far? Again, this should be airtight in your mind, okay? So if it's not, then please ask. Yes?
I don't understand why when we construct m of epsilon to halt, that implies a contradiction on D. It just implies that m cannot exist as a machine, right? So why does us telling it to halt on this input imply the fact that D cannot exist?
We haven't gotten there yet. This is just a contradiction, right? Because m of epsilon loops is one thing we've obtained here. M of epsilon halts is another thing we've obtained. They can't be true simultaneously. That's all we're saying right now.
So all we're saying is that m of epsilon cannot halt.
No, what we're saying is that case 1 cannot happen. D of alpha cannot accept, right? Because if D of alpha accepts, then M halts, but D of alpha is only allowed to accept if M of epsilon loops. That's a contradiction.
But we forced it to halt, right?
Exactly.
We totally said that it loops in this case as well. So
Absolutely, but like we want to prove undecidability, right? So we are very much on purpose building M to be a self-contradictory machine, right? And the fact that we can, because again, just look at the code of M so far, right? This part, we know that's by the recursion theorem. We already proved it. That's ironclad. This, okay, this came from the universe. This is like an if statement. Like, come on, that's definitely totally reasonable. Halt. I mean, that's again like the most trivial thing that a Turing machine can do. Just accept or reject, right? So, like every step of this machine makes perfect sense, like for a Turing machine, right? If D exists, then M definitely exists. You agree? Right?
I guess I'm not seeing like why.
We're not done, just to be clear
I
again.
know, but it's like,
Yeah.
I'm just not seeing like why us telling the machine to halt, like why can't like that statement not be allowed? Like why is it not true that like maybe we just can't say that if except halt? Like maybe that's like the contradiction.
But think about it, right? Like that's like saying, I don't think Python should allow you to say if x equals 1, then return 0. Like that's all this is, right? Like halt is like return 0, right? The if statement is literally like if x equals 1, right? But that's allowed in Python, right? You're allowed to write that, right? So like the contradiction can't be that, oh, then Python doesn't exist. Like that's not true. Like we know Python exists, right? Because you have it on your computer, right? Like you know for sure Python exists, right? The only thing that we don't know for sure is whether D exists, because that's something that the universe gave us, right? And like this Python code is like running D as a subroutine, right?
So basically, given like any valid decider, like I can say to do anything on any condition of the decider.
We can't tell the decider what to do, but we can tell M what to do.
Right, but if D was like a decider that did exist, like given another problem where there did exist,
Absolutely, yeah.
Run any.
You can run it as a subroutine. Again, just think, there's nothing mysterious about this, right? Just think about every Turing machine as being like a Python program. If someone gives you a Python function, you're allowed to call it, right? Just like that. If you give me a Turing machine, I'm allowed to call it as a subroutine, right? Okay, other questions? Yes?
You said earlier, like regarding the run D of alpha, if alpha accepts M halts, but D of alpha can only like, I guess, accept.
Well, I mean, D of M could accept. That's case one, but it's a decider. It could also reject, right? So we just haven't gotten there yet, right? Yeah, we're still in the middle of this. We don't have, like, the code is not complete, right? Any other questions? Yeah.
Real quick, I don't know if this is gonna happen, but someone earlier said that we're trying to prove that M doesn't exist, but we're actually trying to prove that D cannot exist.
Yeah.
And in doing that, we have to create an M that shows that D cannot exist. And so it's not like we get to choose our M to be whatever. I don't know if that makes sense.
Yeah, I hope that makes sense, right? Like our goal is to show that D can't exist. And if we can construct an M that evidences the non-existence of D, then we're done. And that's what we're trying to do. And we're like halfway there, right?
I think where I was running into confusion is like D is not like taking the description of M and like running M. D is like just based on the description of M supposed to come up with something.
Yeah, exactly.
So, like we have no idea what D is or what it does.
We have no idea what D does.
And it like
Right.
doesn't. It's not like D runs M to
No.
see what M does.
Yeah. Yeah.
It
In
just
fact,
should know.
like we know that if D just like ran M, then it won't be a decider, right? Because if M loops, then it's just how is it going to halt,
It doesn't
right?
decide.
Yeah.
Yeah.
So like we know that D is somehow trying to psychoanalyze the Turing machine. Like it's trying to like understand, okay, here's how it works, and it's somehow trying to say that I'm going to figure out whether whether M of epsilon is going to halt or not, right? Somehow. And the universe's promise is that somehow it's going to do it. And as you said, we have no idea how it does it. And in fact, as we will show, it can't do it. Like we will get a contradiction in every case, right? So in fact, the result will be that D cannot exist. Does that work? Yes.
And this is kind of equivalent to the black box thing that we did, just writing it out formally instead of drawing a picture of sorts. Right? Where we just
No, it's actually different. It is actually Fundamentally different. Yeah. And I think let's not spend time on that right now, but I'm happy to talk to you about it. It is actually a completely different way of looking at the problem. Yeah, and it runs into like substantially different difficulties. Yeah, when there are difficulties. Any other questions? All right, if there are no other questions, then let's finish the proof, right? So what's next? Yeah? Mm-hmm. Yeah, and basically it's just an else statement, right? Because that's the only two things that can possibly happen, right? So I'll write it as like else if reject, right? Because we know it's a decider, so it can only have accept or reject. The decider is not allowed to loop, right? Okay, and again, maybe before we get there, let's think about the analysis. And maybe let's write it over here. Right, and so case 2 is that, if D of M rejects, right? And once again, and usually I'm not going to write it out in this much like gory detail, but I want us to do at least one like in full gory detail, and then so before maybe I ask you for the rest of the code, yeah, what does that mean? If D of M rejects, what does that imply? Exactly. Yep. So M must not be in loop epsilon, right? Again, by definition of decider, right? Okay, and this implies? Right, and which again just means it halts, right? Not loop means halt, right? So again, this is, sorry, one second. So this is by the definition of loop epsilon, right? Because that's just what it means for something to not be in the language, right? Okay, and at this point, because now we've taught about it, we're like, okay, Dad, D thinks that we're gonna halt, right? And as rebellious teenagers, what will we do? Loop, right? So again, it's just like, else, while one, nothing, while one, no op, right? Just like have some silly loop here that will just never return a value, right? So when I write loop, that's all I mean, like literally like while one, I don't know, x equals x, right? Just like some trivial loop that you can write in Python or any other language you like, right? So since we have this instruction now, right, we can say, but M of epsilon loops by construction of M, right? And again, that's a contradiction. And now we have contradiction in all cases. Contradiction. Maybe I'll write have contradiction in all cases. And that implies D cannot exist. Right? And that finishes the proof. Yes, question.
It implies D cannot exist because if D exists, then M must exist because our definitions. The rest of the code makes sense, right?
Yeah,
Okay.
yeah. Basically, this code compiles, right? Like if you stick this in your Python compiler, it compiles as long as D is an actual function, right? As long as D is some Turing machine that already exists, right? So it can't be anything else. Like the only thing that we asked the universe for was D, right? Yes?
We have written on our homework where the exam does not do instead of halt or does not halt. So is that still fine? Should we?
Oh yeah, that's fine. Completely fine. Not important at all. Sorry. Yes.
Does it have access to whether the decider accepted or rejected?
Good. So think about it this way: like when we run, like it only has access to that because we ran d of alpha. Again, like if you want to think about it in terms of like Python, think of it as like saying x equals d of alpha, right? And we just see, did it return 0 or did it return 1, right? And then it can use x for the if statement. Does that make sense? Does that answer your question?
Or like, but the if statement is like inside of like our oh, because running D is also in the construction of M.
Yes. Yeah. Perfect. Yeah. But yeah, I mean, if you want to think about it that way, I don't know if this does it actually help anyone. You could kind of think about it as like x equals d of alpha. Is that helpful to anyone? Not really. Okay, that's all right. Yes.
Wholly dependent on the result of D.
Yes.
Why? But then the result of D is like the result of M. Like how can B has the result? Like how can B decide M before like M finishes?
Right. So I think I understand your question, and I think it's like how is this allowed, right? Basically, your question is, come on, there's no way. How can this machine possibly have its own code like before we finished writing the code, right? But remember, we did finish writing the code, right? So now it is just some fixed machine, right? And therefore, via the recursion theorem, which we already proved, right, we can do that. We're just allowed to do that, right? And again, if you unwind it, like that literally means like we wrote this part of the code, right? All the code that came afterwards, right? We finished writing it. That's the T, the Turing machine T. Then we construct our A and B, right? And like this machine is actually going to be A, B, and then like T, everything below here, right? So that's actually what's going on via the recursion theorem, okay? And I know it sounds amazing, but like we proved it. We proved it last time, right? Like we literally proved it last lecture. Yes? Okay.
Well, I think what helped me realize is that like the decider has to work for like, all the machines, right?
Yes.
And we're just finding one possible machine that it breaks on.
Yes.
There could be like a ton of other machines that it does work, or we're finding
Absolutely.
one that does break.
Yeah.
This is why like this predicts necessity.
Yep, exactly. Again, the definition of a decider says that it has to give the right answer on every input. If that input is in the language, it has to accept. If the input is not in the language, it has to reject. That's just the definition of a decider, right? So all we need to do is find one input on which it fails, and the input we construct is M, and indeed it fails on M, right? Yes?
This is a bit tangential, but is the reason, like, following up on his question about the black box,
Mhm.
the reason it's not a black box is because we proved that it's guaranteed to, like, give us, like, something that abides by the rules of the machine.
No, not exactly. Again, let's talk about that afterwards. I know what you're trying to ask. It's just it's too far afield. So I first want to make sure that everyone completely gets this. That is, it looks completely reasonable, and in fact, I hope that every individual step of the proof looks like really simple to you guys, because like each individual step is really simple, right? It is very cool that it all fits together, but like each individual step is actually simple. Yes.
Can we do some practices on other languages?
Absolutely, 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 absolutely. No. We're not only doing this one, okay? I promise you, this is just to get us started, okay? And in fact, I do want to point out a couple of other important things, okay? A couple of interesting things. think about the control flow of this program, right? First of all, observe that we never use the input, right? So the control flow of this program does not depend on the input, which is kind of interesting, right? That means every time we run this program, no matter what input we give it, either this part gets executed or like this part gets executed, right? Like this if statement that depends on like the output of d of alpha is actually like, it's kind of like once and for all, right? Like you once we know what the output is, it determines the way that the machine will execute on any possible input, right? And that's very interesting because it's so different from what you guys have normally seen in your life, right? Like usually if you have an if statement, then like actually at some point, either case will happen, right? Otherwise, why did you put the if statement? Like that's usually how we write code, right? Like you don't usually write an if statement intending that only one of the two pieces of code will ever be run, right? Like that seems silly, in fact, right? But it's important for us because we are doing it for the sake of reaching a contradiction, right? And we have to take care of every case. So this is a different kind of if statement. It's an if statement that addresses our uncertainty as to what this universe-given decider is going to do, right? As opposed to like something that's based on the input, okay? So that's just another interesting point I wanted to bring up. And it's going to be important for us to think through like the control flow of these different kinds of programs, okay? Okay, but shall we do another one? Let's try another language. All right. So I know I usually ask you guys to propose languages, but because I want to like point out a few things, I wanted to suggest a language myself. Although I see some hands in the air now. Yeah. That was my initial plan. But actually, I really want to focus today's lecture on decidability until the very end if we have some time left over. So if it's okay with you, I'm going to, again, just like punt on that, but I promise you we will talk about it. Yes?
Just a question about what you said.
Mhm.
So just to clarify, because it doesn't depend on the input rather than the machine,
Yeah.
regardless of whatever input, you will only choose one of the if statements because the machine
It's fixed.
it depends on the machine level.
It only depends on alpha, which is just fixed, right?
And so that's why last time when we went over that example that didn't contradict both of them, with like the states, the number of states,
Oh, right.
that's why we didn't care about, or that's why like you mentioned something about once one of that happens, the other one doesn't, so like it didn't matter.
Okay, you know what? Maybe we'll come back to that at some point. But I want to sort of keep going a little bit further on this, and then we might come back to like that example of something which didn't work out. Yeah.
Is there a name for this type of proof?
I mean, it's just a proof of undecidability via the recursion theorem. That's all. Yeah. It doesn't have any fancy name as such. Oh, I love it. I mean, the recursion theorem is so powerful. It's so cool. And it's not usually taught. I think, so we're definitely in regime now, which is like not taught in any of the other 181s, as far as I know. I wish it was, though. I think everyone should learn about the recursion theorem. But anyway, let me define a language I'm going to call empty. And this, again, just consists of Turing machine descriptions such that L of M is the empty set. Okay? And again, all we're going to do is try to prove that it's undecidable. Okay? And this time I will say the suppose not. So of course we're going to start with suppose not. And that means the universe gives us a decider for empty. Okay. And now we want to use that to build our machine M. So let me maybe write here, M of X. So, anyone want to get us started? How should we go here? Yes?
Let alpha equal.
Yes, of course we definitely want to use the recursion theorem, right? So again, which is just so cool, right? We haven't decided what we're going to do later, but we know, because we've promised ourselves that we will eventually finish our program, that we can get our own description, right? So that gets us started. Definitely worth a token. Yes? Okay. So let's go ahead and run the decider D on alpha, right? And again, let me kind of write our analysis on the side. And we'll have case 1, which is what if D of alpha, maybe I'll write it more explicitly in the analysis. So D of M accepts. Okay. And does anyone want to tell me, so what does that mean? If D of, do you want to keep going, actually? Yeah. So if D of M accepts. Good. So M is in empty. And what does that mean? L, sorry. Yep, good, right? So again, like we asked the decider, what do you think? What's our language, right? And the decider said, oh, you only accept the empty set. You don't accept anything, right? All right, we are rebellious teenagers, so what are we going to do instead? And maybe I'll just like, oh, sorry. I did not, I forgot to write if accept, sorry. Right, so this is if accept, and yes. Okay, hold on. Let's think about this, right? So what D said is that the language of our Turing machine M is actually empty. We need to contradict that. If we just halted, that doesn't necessarily say anything about the language of the machine, right? Do you want to revise your answer at all?
That means it's non-empty.
We want to ensure that, right? To be a rebellious teenager, we want to write something here that would force the language of M to be non-empty, right? And maybe I'll let you off the hook for a little bit, unless you wanted to give it some thought. Yeah?
Then we accept.
Just accept, right? Let's just accept, and I'm just going to write accept X, just to emphasize that no matter what the input is, we're just going to accept, right? So let's think about that. If we indeed accept every possible input, right, then what is L of M?
The star of
Sigma star. Yep, right? In fact, everything is in the language, right? And that's obviously a contradiction, right? So we've got a contradiction in case 1, right? And now we're going to have case 2, and that's definitely worth a token. Sorry if I wasn't clear earlier. Case 2. So this is the else condition, right? So elf if reject. And And that's again D of M rejects. Okay, so if we're in this case, what does that mean for us? And again, trying to let someone else answer. Yes. Good. So M is not an empty, which means what? Right. The language of M is not the empty set, right? So again, and definitely worth the token, thank you. And like, that means again, the decider is telling us, hey, listen, if there's one thing I know for sure, it is that your language is not the empty set, right? And we are rebellious teenagers, so of course we're not going to let that slide. What are we going to do in that case? What should we do? And maybe I'll ask someone else. Yeah. Yeah, just reject X. Why not, right? Let's just go ahead and reject. And again, I'm going to write reject X just to emphasize that no matter what X is, we're rejecting it, right? And what does that imply? Yep. Right? We're rejecting every single input. So of course the language is the empty set, which is again just very clearly a contradiction, right? And that finishes the proof because again we've reached a contradiction in all cases, and this is the end of the code of our machine, right? Oops. Oh no. Can someone please pick that up for me? Thank you. Thank you very much. Right. Again, any questions about this? Right? Yes?
On something like a test, do we have to rigorously prove that, or can we just be like, look at it and be like, see that it's that?
If you wrote this and you wrote this analysis, just like this shorter version,
Yeah, like we don't have to prove that
totally
the
fine.
language of them is the empty set for the reject. Like we can just be like, look at it, yes, this is true.
I mean, you could draw the arrows or just say like by construction. Yeah. For something where it's so clear, that is definitely enough. Yes? Mhm. Absolutely not, right? Because this is the code of the machine, right? I'm really glad that you brought that up because I've seen this on some final exams and we had to like take away so many points, okay? Like if you just wrote here, if except, then L of M equals sigma star, that's meaningless. Like that's like writing in the middle of your Python code, if X equals 1, then L of M equals sigma star. Is like, what? That does not compile, right? That is not a thing that a Turing machine can do. A Turing machine can accept, it can reject, right? Like those are the things it can do. It can execute arbitrary logic, right? But it can't force something. So I'm glad you asked that question, and it is very, very important that in such a construction you actually use words like accept, reject, or some other logic, right? Let me ask you guys one question, because I don't see any other questions from you. Oh, I do see one. Okay, there we go.
So for the decider,
Yes.
accept case, we decide that we're going to accept X no matter what X is. Would it still be okay to just accept like any arbitrary like string, since that was the only non-empty setting?
Wonderful. That's exactly what I was going to ask. So I'm glad you suggested it. What would you like to put here instead? 0. 0. Why not? Right? So if we change that to accept 0, the only thing that would happen is that now instead of L of M, and sorry, maybe just to be more clear, right? What we're really saying here is accept if and only if X equals 0, right? And otherwise reject. Right? So if you write that here, that I only accept 0 and I reject everything else, then the language of M, as you said, would just be 0, right? Which is still not the empty set. So it's still a contradiction. So this is another variant that works just as well and definitely worth noting. Okay, so like that's a very important point I wanted to make, is that we have a lot of freedom here, right? We actually have a lot of freedom in this particular example, at least, with the empty language, right? And that's something that you're going to encounter with different languages, that there's more or less freedom in terms of how you construct the machine M. Any questions about that? Does that make sense to everybody?
Are we assuming alphabets to always be 0 chance?
I guess here we're just assuming that 0 is a member of the alphabet, which is fine. You don't have to, like, you may always assume, okay, for any question that we ever ask, if you don't specify the alphabet, that you can assume that like 0 and 1 are definitely in the alphabet. And if you want to assume other things, just write it down. Just be like, I'm going to also assume that something else in the alphabet, right? Okay. Everyone good with this? All right, I like it, I like it. I see that there are some lean, mean undecidability machines starting to form in the audience. Let's keep going, okay? Unless there are, again, any other questions? Okay, very good. So, and again, I know usually I let you guys propose languages, but again, in the interest of making sure that everything is super clear. Wow, it's terrible. Let me suggest another one. So EQ. In this case, I'm going to have 2 machines. And the pair of machines is in the language if the language of M is equal to the language of N. Okay? And I once again want to prove this is undecidable. Just undecidable today, mainly. Okay. So again, as usual, of course, we'll start with suppose not. And that gives us a decider that the universe provides for EQ. And now we build M. And again, the first step, of course, we're going to just let alpha be our own description by the recursion theorem. Okay. But now what? Now how are we going to address this problem? Yeah.
I'm thinking, is it possible if we have another machine?
We definitely need, in fact, to make another machine, right? Because so far we only have ourselves, and D will require 2 machines, right? So we better build another machine, right? So okay, so let's go ahead and let N be a Turing machine such that what? Like, what's the code of N? What do you want it to do? Yeah, why don't we just make it reject everything, right? Such that N just rejects always. Right? And we have a lot of freedom here, but this is certainly allowed, right? All right, I love it. Got us started. And give me a moment. Is this? Very bad. Okay. And I'm just going to write the analysis over here. Right? So the analysis is that, like, by construction, right, L of N is the empty set, right? So at least for one of our machines, we know exactly what its language is because it just rejects always, right? This is completely allowed, right? Within, it's like, again, it's like, think of like a Python program, right? Within a Python program, you can just have a string that like defines another Python program, right? So that's all we were doing here. Let me see, pick one of you guys arbitrarily. You. Oh, okay, sure. Yep, let's go ahead and say let beta equal the description of n. Okay, and then you want to keep going? Right. So we run D on alpha beta, right? And suppose it accepts. So let's think about the analysis here, right? Let's write it as case 1. D of M accepts. So yeah, what does that mean? If it accepts? Yeah, so the language of M has to equal the language of N, but the language of N we know is empty, right? So once again, you know, we ask the decider, what do you think about us, right? And it tells us, well, I think your language is going to be empty. And of course, we are very rebellious teenagers, so what should we do in that case? Yeah, so once again, we can just have it be like accept X, right? And, right, so by construction, we have that L of M is sigma star again, right? Just like in the other case. And again, that's an immediate contradiction, right? Okay, and maybe I'll just stick with you. What about in the other case? Yeah, sorry, let me just write that out. So else reject. Okay, sorry, I realize that's very confusing. Else if reject, right? Because again, it's a decider. Only has 2 cases, reject and accept. In that case, okay, but again, let's just do it more slowly. So again, case 2 is D of M and reject, right? And what does that imply? Yep, is not equal to the language of N, which of course we know is the empty set, right? So once again, it's basically the same thing as we had in empty, right? And what do you want us to do in this case? Just reject, yeah. Right? And having done that, we can say that the language of M is the empty set, which again is a contradiction, right? Because the D just told us that it's not the empty set, and now we have constructed it such that it is the empty set. And again, we have a contradiction in all cases, and that finishes the proof, right? So even though this problem seemed a little more complicated because it had like pairs, it really wasn't all that complicated. The only thing we needed to do was just build a Turing machine along the way, right? Any questions about this version? Yes?
Really quick aside.
Yeah.
I see where I was going earlier, but this one is kind of like the black box because it, at least the way we constructed it here, it would show that that one would be true otherwise, right?
It is definitely a little more black boxy in that way, but it's still fundamentally different, which I will talk to you about afterwards. Yeah, I'll just show you an example, which will make it clear. Yes? Yeah, yeah, that's right. That's right. And I like the way that you put that, right? Is that if we had just made n a little more complicated, right? Then in the reject case, we do want it to behave identically as n. So like in general, instead of writing reject x, we could kind of write here, and I'm just going to kind of use C language, right? We just like return n of x, right? We're just like passing control to n to ensure that L of m will always equal L of m will always equal L of n, right? So that's that you're exactly right about that, right? And this is like one way that you could write it if you wanted to. And very nice, definitely worth the token as well. That's a really important point that like what we're really doing here is just trying to like imitate whatever n was doing. Yes.
I don't know if this is like useful, but like for this proof, you need two different machines, like wrong or right.
Mm-hmm.
Are you allowed to use the decider as one of those machines?
You are allowed to say like run the decider on itself as one of the machines. I don't know how that would work. Like I don't have a good example of where that could be useful. But thank you for giving us an idea for the final example. No, I don't know. We'll most likely not. But yeah, we'll keep that in mind. I don't see immediately how to do that. How do you make use of that? Yeah. Any other questions about this? Does this make sense? Yes.
This problem in the proof, we were like arbitrary, not arbitrary, but like we're able to like decide what the language of M is.
The language of N, you mean? Yeah, right? The language of Nancy. N is a Nancy, just because like, yeah, we're just constructing it inside of this machine. Yeah.
And even in like the cases still, like the machine like M for Macy is like you're also defining that to be like M, is that right?
Well, that is kind of more like the other cases, right? Where it's like depending on what the decider does, we choose the behavior of M, right? But yeah, N we kind of just fixed ahead of time. Yeah. All right. Okay. So I want to kind of challenge you guys a little bit more and give you one of the problems that we had in one of the, it's actually in one of the practice, finals that we gave you. Okay. So let me write it here. So we called this the love language. Okay? So the love language is m comma n such that the language of m is only n and the language of n is only a description of m. They only have eyes for each other. Okay? So let's try to prove that this is undecidable. And of course, the proof will start the same way. Suppose not. There exists a decider. Okay. And let's think now, how would we build our machine M? Let me again start with our own description. What do you guys think? How should we attack this? Do you have a hand in the air? So, any ideas? Anyone have a thought? An attempt? Yeah? Okay. Excellent. Yeah. So, okay, his observation is that, look, even though we haven't written the code for M, we have our own description already, right? So why don't we just make N be the Turing machine such that what? It only accepts alpha, right? So basically, N of X just says if X equals alpha, right? Then accept, else reject. Right? Excellent idea. Very nice idea, right? And let's just again think about that in terms of the analysis. So by the construction of N, we know that the language of N is indeed only M, right? So we know that N really likes M for sure, you know. One direction of this of this is guaranteed, right? N definitely likes M, okay? But we don't know about the other way around, unfortunately, right? So that's what it's going to be something we're going to have in our control. Definitely worth a token. Okay, that's just a yes. Okay. So let's go ahead and run D of alpha comma. I'll just write description of N, right? And just for technicality, I should put another parentheses, right? Okay. So if accept, okay, and let's just again, and definitely worth the token. Thank you for getting this going here. Let's think about what that means, right? So if D of M and accepts, can you help me analyze this? So what does that mean? Yeah? Yeah, then they love each other, right? So L of M should be equal to only N. L of N should equal only M. Now N is already smitten, we know that, right? Because we've already constructed him. But unfortunately, you know, terrible thing. You know, M's dad was like, "Oh, you left him, definitely love it." And unfortunately, M is a rebellious teenager. So, what will M decide to do in this case? Yeah, just reject, actually, right? So sadly, in this case, we can just reject all X. And in that case, right, we would have, but the language of M is the empty set. Doesn't like anyone, right? And that's a contradiction, right? The decider dad was wrong, right? So that worked out. Okay, what if, you know, else, right? If reject, the decider dad is like, you will never, you know, over my dead body. All right, so in this case, so if D of N rejects, right, tells us that it's not allowed, right? So then what should we do? Yeah. Or, sorry, you know what? Sorry, I'm going to let someone else. Yes. Good. So if x equals the description of n, right? I just didn't write beta this time, but yeah, I know what you meant, right? I'm sorry, I'm a little slanted. So if x equals n, then we accept, else reject. Right, and that finishes the code, and that ensures, right, that m only has eyes for n, right? And indeed, well, okay, sorry, I didn't write this case out yet. So if mn rejects, we know that that means that L of m should not equal only n, right? Because we already know that L of n is only m, right? So that already implies it's the only case that can be contradicted. And so then we construct in this way, and that implies that, but indeed, L of m does equal only n, right? And again, that's a contradiction. And we've reached a contradiction in every case, and that finishes the proof, right? Thank you, definitely worth a token, right? Question? Yes?
Proving that there was no pumping lemma, because to say that you can create an end such that it accepts only at least one input, like a pumping lemma would say that there are infinitely many inputs that it would accept on. So like,
Yeah, so just to be clear, there is no pumping lemma for Turing machines. Yeah, absolutely not. Yeah. Note, however, that like the pumping lemma only applies for like long enough strings, right? So it wouldn't like even if this was only some other weaker machine, it wouldn't necessarily imply just from that accepting one thing. But that's neither here nor there. There is no pumping lemma for Turing machines, or at least not one that we have proven. Yeah. And in fact, generally, there just isn't. I don't know of any pumping lemma for Turing machines. Yeah. Any other questions or comments about the proof? For love languages? For the love language, I should say. All right. Yes? Okay, yes, so that's a good point. And I remember we actually had this on one of our final exams, and we intended that this should be the answer, right? But one student did notice that nothing prevents, you know, a self-loving machine, right? Like if m equals n, then technically it is satisfied, right? So you're actually right. The way I wrote it, that should be the case. Now, of course, we could just insist that that's not allowed, right? We could just say m not equal to n. We're not allowed to have self-loving machines, in which case this would be the only solution. But you're absolutely right. In the way that I wrote it, which is the way we wrote it in the final as well, there is a much simpler solution of just sending alpha, alpha comma alpha. Yeah. Excellent. Definitely worth a token for the observation also. Yeah. Sorry? Yeah, I just added it.
I mean, in your M, in the machine definition, do you still need to prove that n is not equal to m, or can you just say since the program looks different, your descriptions are?
Yeah, the description can't be, because like the description of n is a substring of the description of m, right? So it's a strict substring of the description, so they can't possibly be equal to each other. Yeah. But yeah, that is absolutely true, and that would be something you would write in your solution. Yes.
Kind of like get around. You just like be like, oh, n is the same thing as m, but with like a no wall at the end. do in itself and run it like that?
No, I don't think it would be that easy. Yeah, I'll let you think about that offline. Yeah. All right. Any other questions? Yes.
This is like more like in general, but what's like the significance of deciding whether or not a language is decidable or not?
Yeah, so I'm glad you asked that question. Like that's a really, like that's what we've been trying to do from the very first lecture, right? We've been trying to understand what are the kinds of problems that like the universe can solve, right? That no computer can solve. And like the final boss was Turing machines, right? That was like our final boss notion of computation in the sense that we don't know of any definition of a computer that is physically realizable that is not equivalent to a Turing machine or strictly less powerful than a Turing machine, right? So, so yeah, now we have a bunch of examples on the board here, right? And in fact, it turns out that you can essentially characterize this. We won't do it, I think, because I'd rather we think about something slightly different today. But you can essentially prove that any kind of psychoanalysis of a Turing machine, in this sense, like in terms of like understanding what its language is going to be, whether it's going to accept or reject, all these kinds of things turn out to be undecidable because this technique is so powerful. This technique is so powerful you can just directly apply it and prove the undecidability of essentially any kind of psychoanalysis of Turing machine behavior, right? And that's, now we've seen that just with examples, but there's even a way of formalizing this. There's something called Rice's theorem, which probably we won't prove. Maybe we'll do it in the discussion section. I don't know. Might ask the TAs to do it in the discussion section. But one can prove in a pretty general way that almost all these kinds of problems are undecidable. And maybe I'll just say something in words right now. So you guys know the, oh, we won't cover this sadly. I'm really sad about it. Like I really wish we could have time to cover it. You guys know the game Minecraft, right? Everyone knows Minecraft, right? So it turns out that Minecraft is undecidable, okay? In the following sense, okay? And someone's going to make fun of me. What is it called again? If you have a redstone circuit and like something, like what is that thing that appears? Then there's a command block. No, it's like an armor rack or something. Like there's some sort of thing. You guys know anyone know what I'm talking about? No? Okay. There is like some particular canonical object that you can build inside of Minecraft, these things called redstone circuits, right?
The mine shafts. You can make like
Anyway, bottom line is, I think it'll even work with this torch, okay? So basically, the question of, given a particular initial condition of a Minecraft world, will a torch ever appear in like, you know, coordinate 0, 0, 0, right? That problem is undecidable, okay? And the reason why is that you can actually build a Turing machine emulator in Minecraft. So you can take any like Turing machine problem that we come up with and just translate it into like the halting problem, for example, like the looping problem, like the halting problem, and actually build it inside of Minecraft in such a way that like, you know, you let the world there, there's no players, it just sits there, it just evolves according to the rules of Minecraft. And the question of will a torch ever appear here is exactly equivalent to whether or not the Turing machine will halt, right? So it turns out that like even problems like that are undecidable. Like Minecraft is undecidable. And that's because there are always, there's these surprising ways of kind of stuffing a Turing machine into a weird place that you don't expect it to be. There are lots of mathematical problems that are similar in that way. You can kind of stuff a Turing machine into it. And some years I actually do have time to cover that in lecture, but I don't think we'll be able to this year. which it's okay. You know, it's all right. It's all good. You guys can learn about it in other ways. But yeah, that's the answer to your question, right? Like that's what we've been trying to figure out, right? Now, there is another final boss, okay, which we have already introduced, still related to Turing machines, right? Which is just, we've been thinking about undecidability, right? And you guys are now lean, mean undecidability machines, right? Like with this power, with what we've covered today, you guys feel very confident, I hope. If not, then you should ask a question, okay? And all of this works really well for undecidability. But what about unrecognizability, right? So recall from our earlier discussions, right? Love language, yeah. That a recognizer is something that is like a lot, it's a lot less constrained than a decider, right? Because a decider gives you a promise that it will always halt, right? Whereas a recognizer are only promises that for all x in the language, R of x accepts, right? So it does halt and accept if x is in the language. But for all x not in L, R of x is allowed to reject or loop, right? So a recognizer is a lot more, like it's a lot less constrained, right? And what I will say is this, that like, whereas with undecidability, it really just boils down to any kind of psychoanalysis problem will be undecidable. For recognizability, it's a lot trickier to see if something is recognizable or not, okay? And as just like a really simple warm-up that I won't even need to write on the board, think about the halting problem, right? The halting problem is like trivially recognizable. I just run the Turing machine, right? If it halts, then I accept. So for every machine that does halt, I will indeed accept, right? And if it doesn't halt, then I anyway don't ever stop running. So in that case, for all machines that are not halting, that are looping, the recognizer loops. That's allowed, right? So even the halting problem itself is not unrecognizable, right? It turns out the loop version is unrecognizable, but I want us to look at another case that I think is really interesting. And yeah, question? Yes. There's no if. The point is you just lose control, right? So like the recognizer just runs M, right? Whatever the input machine M is, you just run it. And if I lose control, then I'm looping, right? But I'm just allowed to do that. So it's like completely trivial. Like it's just, completely just by definition, right? And actually I want to give you guys a puzzle to think about, and maybe we'll finish it today. If not, then we'll think about it on Wednesday as well. But I think we have like 20 minutes, so I believe you guys can come up with ideas for this. Think about the language non-empty. So this consists of Turing machine descriptions M such that L of M is not the empty set. Okay? And I'm just going to claim that it's recognizable. But of course, I'm going to make you guys think of why. So why? How could that possibly be? Right? First of all, what do we even need the recognizer to do? Like, if we're going to build a recognizer for non-empty, what should it do? Like, what does it need to figure out? Yeah?
You need to find some string using the language that's accepted by
Right? That's exactly right. She's right, right? Like our recognizer R of machine M, right, needs to find some x such that M of x accepts. Right? Or like if it can find it, then it would be able to accept. Right? So basically, R is kind of on the hunt, right, for some input string that M actually accepts, right? And thank you, definitely worth a token, right? So how might we do this? And again, it's okay for us to be totally wrong. If you have an idea and you already know it's wrong, raise your hand and explain to me the idea and why it's wrong. Yeah?
Yeah, I'm kind of thinking like what the only machine that would have the empty set is, and that would just be the machine which always rejects.
Well, it could reject or a loop, right? Yeah, it's not that simple. Yes?
I was thinking just this recognizer just tries beat every single part
Yeah,
of the screen.
certainly why not try that, right? So what if we just say for x equals epsilon 0, 1, 0, 0, dot, 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 right? Just try all the infinite strings one after the other, right? And then just run M of x, right? That's what you're suggesting, right? Okay. Totally worth a token. Thanks for getting us started. What do you guys think? This is going to work? And it's okay, right? Like we have our first idea and then we try to figure out what's going on with it. Yes? What can go wrong here?
Maybe one string, like the first string, will loop.
Yeah.
Give it a chance to try
Right?
the second string.
For example, what if M of epsilon loops, but M of 0 accepts, right? Does that make sense? Then this machine will just never make it past the very first string, right? So this unfortunately does not work, right? Because we could just get stuck, can get stuck on, M of epsilon looping, right? And thank you, definitely worth a token, right? So now what? Yes?
Are we allowed to interrupt the running of the Turing machine while it's running?
Anything you can write as a program, we're allowed to do.
If we can define time,
Yes?
then for each t equal to like 1 second, 2 seconds, 3 seconds, like you keep on running it.
Okay. So just a second, right? So she's coming up with a really nice idea. She's thinking about like time as being one axis, and then strings being another axis, right? And what this thing tried to do is just sort of say, okay, I'm going to start at string epsilon, then let's have 0, 1, 0, 0. Very good. And so on and so forth, right? So what this one tried to do is like, okay, I'm just going to keep running. Let me use a different color. Right, it was like, okay, I'm just going to start running this, right? And the problem is if it runs forever, then we just never make any progress, right? Now, you already gave the right answer, but let me just say another idea that doesn't work, right? Is like we could try to do one step on epsilon, one step on 0, one step on 1, one step on 0, 0, 1. This won't work either, right? In this case, we'll never do more than one step on anything, right? And so her idea is, let's use triangles, right? So the idea is, how about we do one step on epsilon, and that's like a little triangle. Then we do another step on epsilon and one step on 0, right? Then we do one more step on epsilon, one more step on 0, one more step on 1, That's another triangle. And you just keep doing this, right? This is called the triangle scheduling. Right? And the nice thing about it is that for any string, eventually it will get as many steps as you want, right? Beautiful idea. Thank you. Definitely worth a token, right? And so now what does work for the recognizer is just run triangle schedule for m over all strings. And if any accept, then accept. Right? And now we know that if this machine ever accepts any string, this triangle schedule will eventually find it, and the recognizer will indeed accept. The only case in which the recognizer loops is if the machine doesn't accept anything, right? But that's okay. The recognizer is allowed to loop if actually the machine is not in non-empty. In other words, if the machine has an empty language, right? So very, very nice, right? And this just kind of illustrates how non-trivial recognizability can be. Yes? Yeah, it's like if you've ever taken like an operating system class, or even like in 33, right? Like if you're running multiple threads, right? Then you allocate a certain amount of time to each thread, right? So basically the idea is we're gonna have one thread for epsilon, we're gonna run it one step. Then we're gonna start a new thread for 0, we're gonna run it one step, and we're gonna run the epsilon thread one more step, right? So at this point, epsilon has been run 2 steps, 0 has been run 1 step. Then we're gonna start a new thread for 1, run it 1 step, and do one more step on both of these. So now it's 3, 2, 1, right? And in this way, you keep on executing each m of x, right, for like this triangle amount of time, right? That make sense? Yes? Yeah, but I mean, round robin is not the right way to talk about it because round robin usually is like round robin would be the one that just goes forever with one step, right? So. Sure. Yeah. We're just calling it the triangle scheduling. Yeah. I think it's good to have for it to have its own name, the triangle schedule. It's because this is not something that comes up too often in real life, right? Like you usually don't have an infinite number of jobs that you want to schedule so that eventually every job gets run some amount of time, any amount of time, right? But the triangle schedule does have this very beautiful property, right? And so yeah, so this is just like a little taste of recognizability and like the non-triviality of it. How, like with decidability, again, I really hope you guys feel like, yeah, give me any problem, I'll be able to prove that it's undecidable if it is, right? Like it's actually pretty straightforward, you know, to do that. But for recognizability, it turns out to be a much more delicate issue. And questions, yeah. That is unrecognizable? Well, certainly loop is an example of something that's unrecognizable. We can prove that in the usual way, but we'll do that on Wednesday, okay? So you'll see many, like on Wednesday we'll be doing a bunch of examples. Yeah. I'm sorry, guys, I think we have like another couple of minutes, right? So, yeah, can you please say your question again? I just didn't understand. So no, so just like the definition of a recognizer is here, right? So for everything in the language, the recognizer must halt and accept. And in this example, we see any machine which is in non-empty, right? The triangle schedule will eventually find that accept, and it will halt and accept, right? So the recognizer will indeed always halt and accept if M accepts any string because of the triangle scheduling, right? Now, if X is not in L, which in other words, if M is an empty, right? If the language of M is empty, then this will just loop, right? It'll just keep running forever, which is just allowed. R of X is allowed to either reject or loop on any X that's not in the language.
I
Make
think
sense?
we're struggling to understand how you I guess, just come up with triangle scheduling on the fly with the representability.
You just kind of faded out at the end. I just didn't understand what you were saying.
Oh, I just said I think I just like am struggling a bit to understand how like you come up with like triangle scheduling on like a recognizability problem, just like I guess intuitively.
Yeah, basically, I mean, I think it came up pretty naturally here, right? And in general, when you are dealing with problems that deal with like an infinite number of inputs, and you think it might be, you know, amenable to some model of computation, then the triangle scheduling is often very helpful. Yeah. And indeed, it is often very helpful on final exams that I give. Yeah. All right, if there are no other questions, then I'll see you guys on Wednesday. And I have office hours right now.
That's
Yes.